Okay, fine. Yes, so welcome everybody. Those who are not from IIT Ropar, I think there are a couple of students from IIT Ropar, they already know me. But for others, myself Manish Agrawal, I'm a faculty here in the mechanical department. Okay, so we will talk about. Ankurji here is mainly taking care of the thermal aspect of the electrochemical battery molding and its ramification, that how the temperature changes and these things actually do affect in the practical scenarios, right? Here we are not going to go into the thermal aspect. This is mainly is going to be the electrochemical aspect of the battery modeling. Okay, so this is at least, so the overall content is going to be slightly on a mathematical heavy side. So I can make the I will change the communication accordingly. Okay, so feel free to stop me anywhere. There is no issue whatsoever. Okay, and yeah, so I actually work on the mainly on two aspects. One on the or we work on the deep learning aspect of the various physical systems, right? How do we actually can come up with the deep learning algorithm for those? Anyway, but today's topic is a bit different, so let's start. Okay, um, with this. Okay, modeling of battery system, right? And most of the content that I am going to present for the next, it's a very nicely written paper, very comprehensive, uh, written, and quite systematically done the job. And the reason that actually rather than citing it affiliation of this particular paper. Okay, so if you see, some of them are from chemical engineering, some of them are from the civil engineering, some of them are from mechanical engineering, and even I think one was from mathematics also. Mathematics also, right? Electrical, right? So you can see the, so this I put it just to highlight the multidisciplinary nature of the battery research, that actually irrespective to your stream you can contribute into this particular field. And this paper was possible because there were so many different stream people actually collaborated. Okay, so that's the reason, and most of the content on my slide is actually borrowed from this particular paper. Okay. Fine. So before we actually go, so as it is written in the title, we want to discuss the lithium ion battery models, right? So why we want to model, first of all? Why we want to actually design a computational model? What is the need of the computational model? Okay. So why? Sorry. Yeah, you can actually keep on asking or interacting. Why we want to model the lithium ion batteries? So any comment or any input from the audience? Huh? No, I couldn't get. For optimization of what? No, no, but that is fine. That is always the goal of any simulation. It's ready to minimize the experiment. But that is a very generic statement, right? First, the question is why, like, what are the answer we are looking from the electrochemical battery simulation? To understand the quantitative aspect. Okay, so you understand the quantitative aspect, right? Which specifically quantitative aspect? Where we have a list of battery related parameters. Yes. Current density, charge density, charge carrier, charge ability, and other kind of things. So these are actually, in case of lithium ion batteries, these are actually physics based detailed model. Yes. So we are actually going to understand how the things are actually happening in the positive electrode, negative electrode, what is happening in the electrolyte. Right? Yes. So what are the output we are looking for? That is again a bit generic. We ultimately want any system, we want the efficiency to be enhanced, but in specific, what are the output we are looking for? Huh? Amount of the energy stored. Okay, so fine. So amount of the energy or amount of the energy I can draw in a particular cycle. Okay, that can be one of the output. Okay, in particular, let me do it. So ultimately, one of the plot that I am looking for is the voltage that is going to be produced from the battery and the time, or in some way uh, state of charge. Okay. So how the voltage response of the battery? So what is the typical voltage of the lithium ion battery? Anybody know? You want to reduce the pen? You can close if it is creating. Acha, it is not. Sound is not audible. We can reduce this. Is it fine now? So what is the typical voltage of lithium ion battery? Okay, 4.2, 3.6. Okay, these are the typical number. So, but that is actually when the battery is fully charged. Okay, but as the battery when the battery is 100% charged, then the typical voltage is 4.2% voltage. But slowly, actually, the terminal voltage actually decays, right? So the typical graph looks like this. Okay, but this is actually not. So this particular response depend on how much fast you are doing the charging, or actually in this particular case discharging. Okay, so it depend on that. It is not something which is like a fundamental characteristic of the battery that is given to you and that is going to be work for every kind of load cycle. So for example, you see in nowadays there is a lot of emphasis on the battery development, like how fast you can charge your battery, right? You want to charge in 1C, 2C, right? So you want to charge your battery as fast as possible, right? But why not everybody actually just start charging the battery? Like just supply more current, it will charge faster. But there are ramifications to that. Okay, so this actual capacity, one is the theoretical capacity, one is the actual capacity that you actually get out of the battery in a particular condition, right? So that depend on the charging or discharging speed, right? So we want to know that till what charging or discharging rate we can actually draw a sufficient amount of the power, right? Second, uh, for Ankorji to do calculation on the thermal aspect, he will need certain parameter from the electrochemical physical model. For example, the voltage, current, whatever those macro level parameter, right? So those also we want to give it to the thermal model, right? So this is one more aspect. Another aspect, somebody told optimization, right? So ultimately I want to design what is the separator length, what is the porosity of the separator, what should be the again I will explain those things in a more detail. What should be the cathode particle radius or positive electrode radius. So I want to determine all these parameters, and I want to see that how these parameters actually affect my overall battery performance, right? That is one more thing. And lastly, I want to see even how fast my battery is going to degrade. Okay, whether it is going to last 1 cycle, 10 cycle, 20 cycle. Although we will not go too much into the detail of the degradation model in this limited time, but those you can actually model the degradation mechanism along with the electrochemical model that we are actually discussing. So all these things you can do with this physics based model. Okay, so we'll discuss today all these aspect of it. Before we jump into the this electrochemical battery aspect and other things, let's first revise one of the key mathematical concept that we are going to multiple time we are going to refer. Okay, and that is known as Gauss divergence theorem. Okay, so let's just to make sure that everybody is understand that. So let's say there is a one particular arbitrary domain is there which has a volume V here, okay, and or let's call it, let me call it omega to be consistent with the rest of the lecture, and the boundary of this or the area of this I called as a del omega. Okay, these are the typical notation I am going to use. Omega to refer to any domain, capital omega, and the partial of the omega to denote the boundary of the domain. Okay, so you can imagine, for example, this is the bottle, sorry, and the boundary of this, whichever is on the surface, is the partial omega, and overall domain that is there is the omega. Right? Now, the Gauss divergence theorem tells that suppose there is a vector, arbitrary vector v, okay, and I draw a normal n tilde. So n tilde is a unit vector which is normal to the domain boundary. Then v tilde dot n, if I carry out the integration over the boundary, that is equal to the divergence of v over the omega. Okay, just for other understanding, the divergence of the v is defined as del v1 over del x plus del v2 over del y plus del v3 over del z, where the v tilde is vx, v1, sorry, v2 and v3. Okay, so v tilde is an arbitrary vector which has three components, v1, v2 and v3, and the divergence of that particular vector is defined as del v1 over del x plus del v2 over del y plus del v3 over del z, right? So this Gauss divergence theorem, which is written here, what it does, it does something very extraordinary actually. So if you see this integration, this is carried out on the surface, that means here on the surface, right, and this is carried out at the volume, means inside the domain. Now whenever you are carrying out the integration, right, you are actually summing up the things. Integration is like a summation. So when you are carrying out this integration over the inside the domain, it is in the volume, right? So you need the information of del dot v or the v inside the domain, but it is able to convert this del dot v which is inside the domain into the boundary. So here you need only the information at the boundary. Okay, so something for which you need the information everywhere in the domain, you are able to convert to something which you only require at the surface, right? So that's why it is an extraordinary theorem, and it is actually used a lot irrespective to the engineering thing. Okay, so we will not be needing too much detail, but we will just needing the statement of this particular theorem, that is v dot n ds equal to divergence of v over the volume, right? Fine. Now we'll come back to our battery thing. So in battery, if I talk about, so as you can see the slide, there is a word that is mentioned, physics based model. So in today's lecture we are going to talk about physics based model. There are other model, for example, those are known as equivalent circuit models, which are more empirical models. So here we are not going to talk about right now those. There are some data science based model also. Again, we are not going to talk about those. We are going to talk about only physics based model. So the most refined version of the physics based model is known as micro scale model. That is the most detailed one, where you are putting almost everything that is there in the battery in your model. Okay, that is the most detailed kind of calculation that you can do. there is a slightly coarser level of the model that is known as homogenized model, that is the second level of the model. Okay, and so there is a simplification from the micro scale to the homogenized. Again, I will go into the detail as we go along. Right now, just giving the overall picture. Then there is a model called as DFN model, or more popularly known as P2D model. This is perhaps the most popular model that is there for battery model. Whenever you do the electrochemical analysis in software like COMSOL, by default you are using P2D or DFN model. Okay, so this is a kind of 1D model. Actually, it's known as pseudo 2D model. Why it is known? Then again, I will explain to you later. Then there is a more simplification version of that, SPME, where uh, electrodes are modeled as single particle, and then the most simplified form is the SPM. Okay, so we will try to start the lecture with the micro scale version, which has all the details. Then we'll move on to the homogenized model. After that, we will see how you can actually drive the, not actually drive, but at least get some overall steps. How do you go from micro scale to homogenized model, and then homogenized model to how you actually go to the DFN model. Okay, that is the overall idea that we want to cover. After that, this you can do the reading on your own, that how to make the more simplification assumption. So we'll try to cover the first three, that is the goal. Okay, in the next two lectures. Fine. So let's see the schematic first. Let's try to see that what are the things we are going to talk about, right? So this is the overall layout, right? So first I will also try to draw here, and the reason is I would like to at least have some drawing with me when I talk about the equation, and here I am going to write the equation, so let me do that. Okay, so the first thing, let's start from the rightmost. Okay, rightmost and leftmost, right? There are two blocks. These are known as current collector. Okay, so they are just metal strip which are just taking out the current from the lithium ion battery to the external circuit, nothing much. So these are not something fancy, these are quite preliminary stuff, right? Now after that we have positive electrode, right? So this is the positive electrode. I will just denote it with the symbol P. Okay, then there is a separator. Okay, and then there is a negative electrode, which I am going to denote by letter N. Okay, and separator anyway we won't need the symbol, but let's completeness, let's write the S, right? So let's try to see what it is contained, right? So if you see this positive electrode, it is not there is some kind of these particles, right? So I think Ankurji was talking about some kind of lithium compound which makes the positive electrode, if I am correct, some kind of lithium cobalt oxide, right? So these green particles are those only, or any sub alternate to that. For example, I think there is a magnesium MnC, yeah, it is called as MnC. So there also it can be actually particle of those. Okay, sorry. Right. So ultimately, whatever the underlying material is there, these are the particles. Okay. Now you see bunch of black particles flowing here and there. These are binders to keep all these particles, the actual particle where the lithium is there, to hold them together. So these are the binders who are not actively participating in the chemistry of the battery. They are just there to act as a glue. Okay, their role is there. The blue thing that I am showing actually is the electrolyte. Okay, so unlike the conventional picture that you have, that the electrolyte is different, electrode is different, this is not how the lithium ion battery is. Okay, inside the electrode also there is an electrolyte, and actually it is a very important thing to know when you are doing the modeling. So electrolyte is present in the electrode also. Electrode is a porous medium where the electrolyte and the electrode particles are actually present in the same domain, right? And there is another name for that, and these particles are also known as, commonly referred as, active particle, because they are actually actively participating in the overall domain, right? So these are known as active particles. So this is about the this one. The domain, we are going to refer this as a, as I said, we are going to use the symbol omega, and we are going to use subscript omega p to denote the domain occupied by the positive electrode. Fine. Now let's move to the left. So now we have a separator. Again, separator is a porous medium. Here the separator is there and the electrolyte is also present. Okay. Separator job is not to allow the electron, it doesn't allow the electron to move, it allows the ions to move freely, and it doesn't allow the electrons to go from the, otherwise there will be a short circuit, right, between the, in the battery. Now if I go further there on the negative electrode, then I have graphite, right. The negative electrode is typically made of the graphite, C6 sorry, and again there are some binder, other kind of things to keep it together or other things, and again this is also a porous domain. So here also electrolyte is present, okay, and then we have the current collector, right. So the summarizing overall thing, everything is a porous, everywhere the electrolyte is present, okay, whether it is in the electrode region or it is in the separator region, everywhere there is electrolyte, and you have the active particle and you have the graphite here, right. So what are the reaction that are happening? So in case of discharging, so in case of, let's say the battery is fully charged, what will happen that time? Where is the lithium? So if the battery is fully charged, all the lithium is here, right. Now you are discharging the battery, right. So what is happening? Lithium here is actually getting broken into the Li plus and electron, right. The lithium is, positive ions are actually moving toward the positive electrode, right, and the electron are actually going away in the external circuit, and then the electron takes the whole path, come back here, and then Li plus electron again make the lithium, right. Okay, fine. So in electrode, if I see, there are two things that are moving. What are the two things that are moving? One is lithium, not lithium ion, okay, lithium and electrons, okay. Lithium ion is not moving, right. Lithium ion is, huh?
Electrons in lithium ions.
No, lithium and electrons are moving. Lithium ions are moving inside the electrolyte, okay. These are the two things which are moving in the electrode, okay. And what is moving in the lithium ion is moving in the electrolyte. We should know that which species is present in which domain, then only we can actually do the we can develop the model. So lithium ions are moving in the electrolyte. Apart from the lithium ion, which are known as cation, because these are positive ion, they are negative ions also moving, okay. For example, if you have LiPF 6, then it is I think LiPF, right, Li plus PF negative, sorry I don't remember the exact formula, LiPF 6, and here also it will be PF6, right. Thanks, right. So there is a cat. So in electrode we have lithium and electron. In electrolyte we have the lithium ion and I am writing X minus some kind of anion. Okay, so this is in the electrolyte. Fine. So let's go to now again. Sorry. Acha, new one means this is what. Fine, thanks. Okay. Fine. So now let's talk about the electrode, right? And then we'll go to the one. Right. So in electrode, first talk about. So let's talk about the conservation law in electrodes. Okay, sorry. Let me know because sometimes this pen is not writing it. Okay, so first talk about there are two species. One we are going. So let me define something. You know what is Faraday constant? Or you know first what is mole? What is 1 mole? There is a number, right? 6 point. 6.023 into 10 to power 23. Right? So 1 mole means this is number of atoms of that or molecules of that particular quantity, whatever is the quantity. So this is rather than being this is just the actual number, not the mass or something. Okay, and the Faraday constant means the charge that the electron is 1 mole of the electron carries. Okay, that is the Faraday constant, amount of the charge that is present in the 1 mole of the electron. Okay, so conservation law in electrodes. Fine. So let's talk about the 1 second. Lithium. Fine. So now let's see. I have drawn, right, that there are a bunch of active particle, right? Okay. Now in this bunch of active particle, I am taking a small domain here. Okay. So the domain is even smaller than the any of the particle. Right? And now if I take this domain and again draw it. Okay. Let me draw it in a more complicated way so that you don't confuse with the active particle. Okay, so then there are two things that are happening. One, the lithium ions are actually moving out, right? I'm just by convention I'm taking the moving out thing. If I take the negative of that, that is a moving in thing, right? So the moving out, I'm going to denote the flux as N tilde lithium. That is the flux. And you know, you understand the flux, right? For example, if there is a pipe flow that is happening, right? And then what will be the flux? That will be the velocity into the area, the amount of the flow that is actually happening, right? So this is the flux that is happening, and the concentration of the lithium ion I am going to denote by CLI. It's not. Okay, I have to write it very slowly. So this CLI is the concentration of the lithium. Okay, the unit of that is mole per unit volume. Okay, so the unit is of the concentration is mole meter minus Q, right, per unit volume, right? So now let's do the mass conservation. Okay, so the amount of the lithium that is there inside the volume is the concentration CLI, integration of this okay, or you can note it by dV. Okay, this is the total amount of the lithium that is present in this volume. Okay, and what I am doing, I am writing the derivative with respect to the time. Okay, how much it is changing. So rate of change of the lithium mass, that should be equal to the amount of the lithium that is going away. Sorry, actually it should be the negative of the amount of the lithium that is going away, right? So then it will be minus of n tilde Li dot n. Okay, what is the flux? Right, flux is a vector, and then I am taking dot product with the normal, because whatever is happening in the tangent direction, that is not going to go out, that is just going to be remain within the boundary. So that is the one, and then I integrate it over the whole surface, and that is actually this one. Okay. Now what I do is I apply the Gauss divergence theorem. So then it is going to be del C Li over del T. I take this derivative inside the volume, plus I take this quantity on the left hand side and I apply the Gauss divergence theorem. So this will become divergence of n tilde Li dV, because now I have converted the surface integration into the volume integration. Now if I combine these two terms, then it will become del C Li over del T plus divergence of n Li, that is the flux overall thing, into dV over equal to 0. And because this is an, now I don't want to go to the mathematical argument too much, but just for the completeness, because this is an arbitrary domain, I can actually conclude that the integrand of this is actually equal to 0 when this integration is 0. So then this is going to be del C Li over del T plus del dot n Li equal to 0. Okay, so this is the conservation law for the lithium inside the electrode. Fine. This is actually although we have, out of the 4 things, or actually in total there are 6 things, this is the standard form, and this will be the form that is going to keep on occurring again and again. Okay, so the main thing is to understand this particular relation. Yes. Yeah. Yes. dV is the volume of the arbitrary small, infinitesimally small domain. Okay, domain. ds is the surface. No, no. So in general, the theorem applies for any surface or something, but here the discussion is restricted to the electrode particle. So this is the electrode particle. Inside the electrode particle, I took a very small domain. Okay, so that's why I have drawn here, right? So from here, this is the one. Okay, and then this is the domain I am talking about. So this domain is actually the omega, and the boundary of this is actually the partial or del omega actually. Okay, no, this boundary is arbitrary, but it's not changing. Okay, the boundary I am, it's not a moving particle I am taking, or it's not a deformable domain I am taking. So this boundary is fixed with the time. That's why I can take the derivative inside the domain without any issues. Okay. So just for if you want to connect, you know the heat transfer equation, right? So in the heat transfer also, just to quickly connect with other things, if you have a domain, you have the heat that is going flow out, that is q dot n. Inside the heat that is changing is rho Cp del T over del T, assuming the rho and Cp is constant with respect to the time. That is the heat that is changing in the volume in the domain, right? In the total domain, and that I can actually equate to minus q dot n ds, and I can do the same step, and ultimately I will get rho Cp del T over del T plus del dot q equal to 0, which is actually the heat equation. Okay, so this particular form is very common. It is not it. If you drive the mass conservation, again you will have the same kind of form. In heat equation also it is the same form. So the steps are actually used in various domain, and the form that you will get at the end is going to be more or less similar. Sometimes there may be vector, sometimes there may be tensor, that is a different thing, but at the end of the day you will get always the same form. Okay, so you can relate with the heat equation also. It is the same thing, right? Rho Cp del T over del T. Here the temperature is there is the concentration, there is the heat flux, here there is a mass flux. Otherwise it is the same thing, right? So it's not something very new. Those who are familiar with the heat transfer, they have been seeing this kind of equation anyway, right? Okay. So now the lithium is done. Now we'll move to the second species, which is electron. Okay, again I don't, the good thing is I don't again need to drive. Conservation law is same, only thing is there it was concentration of the lithium, here the concentration of the electron, nothing else, right? So then, so now let's talk about the electron conservation. So then it is going to be del C E minus by del T plus divergence of n E minus tilde equal to 0, right? Same thing again. The only difference here is actually this term I can drop off to 0. Okay, and the reason is the movement of the electron is so fast that this phenomena, this time scale, the time scale of this is in the millisecond or the nanosecond. So you don't need to consider the first term. Okay, so this equation becomes even more simpler compared to the previous one, and that is the divergence of n E minus tilde equal to 0. Fine. So if you want to call the, so this is all in the gamma k domain, where k is either p or n. Okay, so whatever the equation we are driving, those are valid in the electrode region, either positive electrode or the negative electrode. So that's why I am calling that this is for the omega k region, and this is the second conservation law that we have obtained. Okay, now let's talk about the third one. Okay, so we, in a battery, we are not only interested in the chemical stuff. There is a something called else is happening, that is the electrical stuff, right? We want to talk about the potential, we want to see what is the voltage difference, how the currents are moving or something, right? So we want to do the conservation of the charge also. Okay, so let's take the, so conservation of the charge may be different from a conservation of a particular species, because huh? Because this okay, so let's say here the this, you know, right, d dot q, right? You know what is q in general? Heat flow. So Fourier law of heat conduction says that q is equal to minus k dt by dx. If the k is very high, how much time it will take for the steady state to reach? Very fast, right? Instant and it will reach, right? So this is also like this, that the diffusion of the electron is very fast. The diffusion constant of the electron is very, very high. So it will be so fast that you don't need to consider. Okay. So ions are moving at the time scale of second, electrons are moving at the time scale of microsecond and the nanosecond. So you can neglect the time difference. Okay. So it is so fast that for you it is stationary. It's not uniform, it is changing with respect to x. Time derivative is 0, so it is changing very fast. So that's why the time with respect to time it is uniform. It is reaching the steady state very fast. Okay. So del dot n equal to 0. Now charge conservation. So in general the charge conservation is del q over del t, that is the total charge that is changing with respect to time, plus del dot the divergence of the current equal to 0. That is the charge conservation typical equation again. Okay, because the current is like a flux. Okay, and q is like the total amount of charge. What is the charge actually in our case? In our case the total charge is, in case of electrode, there is the only electron which is charge carrying species. There is no lithium ion in the electrode, there is no anion in case of electrode, only electron is there, right? So q is simply F Faraday constant into C into E minus. Okay, so whatever is the concentration of the electron, if I multiply with the Faraday constant, then I will get the total charge, right? So if you see, if del C E by del T is 0, then del Q over del T also will be equal to 0, right? Because both are the same thing, just multiply with the constant. And other than that, even the second equation that you will get is del dot I tilde equal to 0, right? And this is actually same as del dot F CE minus equal to 0 and del dot CE minus equal to 0. So both this one and this one are actually identical. Oh, sorry, I think I did something. No, 1 second. Sorry, this is not. This is the flux, right? Sorry. Okay, fine. So we have derived 3 equation, but we need only 2 equation because one is actually dependent on another. Okay. So I think I may have it in the slide. Okay, so although I will again refer to this one, but in order to summarize, these are the 2 equations that I am talking about. The first 2 equation, we have not talked about the rest of the stuff yet. Okay, this is the final one which we will discuss at the end of the lecture. The goal is to cover the full slide. Till now we have been able to cover the first 2, this one and this one. Okay, so these, so ultimately in the electrode I have to solve only for the conservation of the lithium and the conservation of the charge, and the first equation is the conservation of the lithium and the second equation is the conservation of the charge. Okay, these 2 are the governing equations. Now okay, I should check the time and then I can, okay, still time, I think we can easily cover. So what was the unknown in the 2 equation? There was a C E, sorry, C lithium, that was one of the unknown. right? Another unknown was flux n tilde lithium ion. Another one was current, right? But the uh, two equation cannot be used to find the three variable. So we need the some kind of relationship between these two variables, right? So the now comes the second one, the what are known as constitutive law. So the NLI tilde is equal to minus D tilde. This is C comma X. Okay, I should actually use the K also, but it's okay. And then I have the gradient of C, right? I think that is fine. Okay, so the flux of the lithium particles or lithium molecule is going to be related to the concentration through this manner. You have seen this law, right? There is a name to this, Fick's law, right? So it is saying, if I can write in the 1D form. So in 1D form it is going to be minus D into del C over del X, right? The way the heat transfer happen, right? From a high temperature to a low temperature. Similarly, if you have two species, right, where one place has a higher concentration, another one is lower concentration. If you take a salt in your kitchen, right, and you put somehow you actually manage to have a you take two solution, one which has a high salt concentration, another has a low salt concentration. You pour them, right, and leave it for some time. They actually will become, over a period of time, the salt will diffuse from a high concentration region to a low concentration region, and there will be equilibrium will be reached, right? So like the way in the heat transfer from a high temperature to low temperature, right? So here also the same thing, right? I am just writing in a more generic 3D equation, that the D into this one. D is known as diffusion coefficient. Now the tricky thing about this D is that the D is actually depend on the concentration. Okay, so whatever is the actual concentration of the lithium in the electrode, the D also depend on that. Okay, so there is a I think I was talking there was a podcast by Elon Musk where he was talking about this, and he gave a very nice analogy. So I will repeat that analogy. So it's like so this is what this law is dictating. It is dictating that how the lithium is actually getting inside the anode or in the cathode, right? So when you are doing the charging, so the lithium is coming and it's trying to go in this graphite seat where to actually go and park myself, right? So try to imagine a parking place which is first empty. So then you will easily find a space and you will park your car and you will go, right? But if the parking space is full, right, then it will take a lot of time for you to figure out where to park myself, right? So if the concentration, so that's why the diffusion coefficient is a function of the concentration, and actually keep on going down in general as a function of the concentration. And the ramification of that is, if you see your phone, if you notice the charging of your phone, that 80% charging actually happen very fast. The rest 20% charge takes a lot of time to happen, and that is actually physically that is happening because this diffusion coefficient here is actually a function of the concentration. That's why this is happening. If the diffusion coefficient is independent of the concentration, probably you will not see that kind of thing. Okay, so that's why it's very important. Although a lot of in the literature, a lot of time we just take it as a constant, but actually in general, especially if you are not worry about the 80 to 100% charging, you just want to see the 0 to 80%, you can take it then constant. Right? So this is the constitutive law for the lithium one. For the electron, the law is again, I think all of you might know, this is conductivity as a function of x and then this is del phi, where phi is the electric potential. So you know the Ohm's law, right? I equal to so that is also that is the same form. So if you take this on the other side, then okay. So this is a microscopic form of the Ohm's law. Okay, that is more macroscopic law. If you integrate in everything, then you will get it. So this is the point-wise law that you can apply in the domain. So this is known as also Ohm's law. Okay, so this is sigma. So this is conductivity. Fine, this is current, and if you want, you can put it IK. This is not. If you want to denote that where this current is there. What are you saying? No, need not to be. Current is a vector quantity in this case. Right now it can be drawing in any direction. It is a vector.
Among the partitions, it can be on any axis. Among the three quadrants.
It can be in any. Right now. Later we'll make, in actual battery it is actually more or less one directional, but that will go later. But right now we are assuming for the model it is an arbitrary vector. Not a okay. So I am keeping the subscript k here so that to indicate that we are still talking about both of the electrode. K can be p or n. Okay. So this actually complete the picture for the electrode. Now we have to go to the electrolyte. Okay. Electrolyte, the story is unfortunately slightly more complicated compared to electrode. Okay. So in electrolyte now, but the thing is we have done some groundwork, so now we can move faster, although the things are more complicated. So now we have in case of electrolyte we have Li plus, anion, okay, and we have the charge. So again three governing equation. Let's write down all the three, and it should be fine, right? So in Ni plus is also same, del C Li plus. The only thing is now I am writing plus because now the conservation of the lithium plus ion plus del dot flux Li plus equal to 0. Same form, right? Just the SPC is changing. Similarly, del C x minus over del T plus del dot and tilde x minus equal to 0. Same again, similar form. I will write here the last one, that is the conservation of the current. Okay, here the current here is Faraday constant into n of Li plus minus of n tilde of xi. Okay, so the current in the electrolyte is not happening because of the movement of the electron, it is happening because of the movement of the ions. Okay, fine, and they are current due to the movement of the positive ion, and there is a current due to the movement of the negative ions, and definitely the charge, the direction of the current is going to be negative of each other. So that's why there is a F n Li plus minus n xi minus, right? Okay, so this is the current, right? So now if you see again, if I know this, I can, if I know 1 and 2, I can get 3, right? Because see, if I know the current and the flux of the positive ion, I can calculate the flux of the negative ion simply. So there is no point again to solve the 3 equation. I can only solve the 2 equation and I will be done, right? No, no, no. It is right now we have not gone to the homogeneous problem. Electrolyte is present everywhere. So these are the equations that are valid anywhere in the electrolyte. Okay, whether they are that electrolyte is present in the electrode, it is present in the separator, wherever it is present, these equations are valid. Okay, fine. Now, similar to the Fick's law that we saw in the last, in case of the electrode, let's talk about the how to relate the concentration and the flux in case of electrolyte. So then it is going to be N tilde Li plus is going to be minus D. Here I will write E. This I think we don't need to keep it as a function of the concentration that much. 1 second now. Minus dE del C, the concentration of Li plus okay, plus overall plus, and I have T plus I E divided by Faraday constant. Let me just confirm this one. Mostly it should be right, but still, so that I don't tell you anything wrong. Yes, it's fine. Okay. Let me have you the okay. This one is fine. Okay, so the first term is similar to electrode case, where there is a due to the concentration gradient, there is a movement of the lithium plus ion that is happening. That is same as the previous case. There is the additional term. Okay, so here even if the concentration gradient is 0, there is going to be the movement of the ions, lithium plus ion, and that is due to going to be the electrostatics or sorry, the electrical stuff that is going on, the amount of the charge, the current that is moving, right? So this T plus is known as transference number, which is generally given, okay, and it can be calculated experimentally. Okay, the typical value is around 0.35, right? And F is the Faraday constant, I is the current. Okay, so again we are able to relate the flux and all those things. Now the last thing that we need is how the I thing is there. So I E is minus sigma E, and this is del phi E, okay, plus now this is one I always forget, other things I remember. So this is slightly more complicated. Minus 2 by F 1 minus T plus and del mu E. This also can be written as minus sigma E del phi E minus 2 by F 1 minus T plus d mu E over d C E and del C E. Okay. So if you want, you can focus on the last one only. Although the last one is also fine. So where the mu, anybody know, that is known as chemical potential. Okay. Again, we will not go into those much detail. This is the overall relationship. The main thing that you have to notice here is the in case of electrolyte, the the current is depend on the voltage difference, the potential gradient, as well as on the concentration gradient, right? While in case of electrode, it was actually dependent only on the potential. I can actually go to the summary slide. right? So we have done quite a bit of, this is the electrode equation, this we saw, right? This we know, the current charge conservation, this is the constitutive law, this is how the current is actually dependent on the electric potential. Again, electric potential, you know, right, the amount of the work that is required to bring the unit charge, right? So this is what it is. Now this is the electrode equation, these four, these are the electrolyte equation. So del dot, this is the conservation of the lithium plus ion, this is the conservation of the charge, this is the constitutive law relating the flux of the positive ion with the concentration gradient as well as the current, and here the current is again related with the potential gradient as well as the concentration gradient. So this actually these two, these four are the actually partial differential equation that you have to solve in order to simulate the electrochemical phenomena in the lithium ion battery. Along with this, two here and two here, four constitutive law. These are the equation that you need. Okay, fine. The main thing to remember here is, here the constitutive law is very simple, and the reason is, in case of electrode only the electrons are moving, while in case of electrolyte the things are much more complicated because the movement of the current is generated by the cation as well as the anion. Although we are not going into the electrochemistry that much, but because of that the constitutive law underlying actually becomes much more different, more complicated, and the current is actually a function of the chemical potential also. So again, how the mu is related with respect to the concentration, those there are some simple laws. The most simple is the assuming the electrolyte is the ideal, which assume that the overall concentration of the lithium compound is much lower, then that is actually has the mu here is mu naught plus RT ln CE. Okay, this is the simplest law that you can assume. There is a more complicated version of that also. So the chemical, ultimately the chemical potential is also a function of the concentration of the species. So these are the four equations, and if you solve them, then you will be able to simulate the electrochemical phenomena. Okay, so at least 60% or 70% of the story is completed. So I am just stopping if there is any doubt or comment. Hmm. 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 इसका इसका so what it is saying, that the flux, there will be a flux of the positive ion even if the concentration gradient is not present. Okay, so because if the this del C term is 0, then the concentration gradient is not there. That means everywhere the lithium plus ion concentration is uniform in the spatial domain. Then also there will be a flux of the positive ion, and that will be because of the this particular quantity. So this current IE, that is made of two parts. Okay, that is made of, that it is getting generated by the movement of the positive ions as well as negative ions. Now this T plus number or the quantity is known as transference number. Okay, so this T plus actually denote that how much of that. So if I say T plus is 0.3, that means 30% of the current is carried by the positive ions. Okay, if the T plus is 7.7, then the 70% of the current is carried over the positive ions. So this is kind of, if you say one second. Okay, so this is kind of the current that is carried over the positive ion, and if you see in the denominator there is a F, which is a Faraday constant. So that it, so if you have the amount of the charge that is carried out, if you divide by the Faraday constant, then you will get the number of the mole that is getting transmitted, right? So that's why I am dividing by the, or we are dividing, not I am dividing with the Faraday constant. Okay, so here the overall, there is the chemistry part that is actually playing because of the anion and cation. right?
Is there any equivalence of the transference number in heat transfer?
No, I don't think so. Yeah, even I don't think so.
In heat transfer, that equation will, the right hand side will only have the first term.
Yes, yes.
Second term is
Will not there. Oh.
because the amount of heat that is
Hmm,
moved does not
hmm,
depend on the
hmm,
absolute
hmm,
temperature,
hmm,
it only
hmm.
depends on
On the grid. So this will not be there.
The second part is actually what is coming because of the generation of Pl6 negative in the electrolyte.
So because there is a negative ion that are there because of that. So even my electrochemistry is very like not that. No, I will not say great, not even good in that way. I just know the mathematical equation. So yeah, maybe chemical scientists can give a slightly better physical intuition than me in terms of answering this one. Okay. But yes, there is. So now once we have the equation, what do you need? You need, the story is not complete only if you have the equation. You need boundary condition as well as initial condition. Here the initial conditions are fairly right. These two are not independent, right? One is in the electrode domain, another is in the electrolyte domain, but they have to talk with each other in some way. The lithium conservation of the lithium, there has to be some kind of talk that has to go between the electrode and the electrolyte, right? So that actually goes through what is known as famously known as, okay. So the Butler-Walmart equation, I don't know whether I should write it. It is already written here. I can skip the hard part and I can refer here. So, but anyway, let me so to the. So this electrode particles are there, right? So if you see this boundary, right, at this, so this reaction, lithium is decomposing in the lithium plus electron. Everything is happening at the boundary between. So this reaction that is happening, that is the one which is actually the main driver of the current, right? If this reaction doesn't happen, the current is not going to get generated in the lithium ion battery, right? Light, and that torque is actually quantified by the equation, the below equation, and this equation is known as Butler-Walmart equation. Okay, so what it says is the which is a constant sine hyperbolic into f by 2 RT and eta k. So eta k is what is known as over potential at the boundary. Okay, at the point that you are talking about, at the particular boundary, what is the potential? Phi k. What is the potential of the electrolyte at that particular point? And minus particular concentration, right? So although I have not defined the open voltage like when if you see for a define a open voltage for a battery, that is the voltage that is generated when it is almost not giving any current. Okay, so if you just connect the multimeter there, it is the open voltage for that particular electrode. Okay, that's why there is a subscript k. There is the jk naught, which is the constant. That is the in some way if the eta k is 0, then this particular quantity sin hyperbolic 0 will become 1, and then you will get jk naught. Okay, so that is the current that is drawn if the in the equilibrium state. And this is a famous Butler-Warmer equation that is there, right? So yes,
What is the origin of the Butler-Warmer equation? Where does it come from?
I don't know. I kind of phenomena. As far as I understand, in my limited understanding, even there is a lot of open question like how this kind of phenomena happen. Even there, the understanding of the like chemical people are quite limited. It is more, I think, the way it was given. It was more. But this tells you that uh, as much the higher is the over potential, that means the higher voltage difference you apply, that much it tells you. And yeah, it is a slightly simplified version of the Butler Warmer, but I think that is fine for this lecture. You can see sometime it is not 1 by 2, it is that's a 1 by 2 only, so I think it is fine. Okay, more or less done. Little bit more and we will be done with the stuff. So let's talk about all the boundaries, right? So we have two things. We have phi as unknown potential, and we have the concentration, right? So we talk about this lithium. One second, I should have one question, or I have. This is this is Faraday constant. I can one second. This is actually very sensitive. Okay. So at the boundary, you have the current that is flowing out, right? So that means if I take the current IK, take a dot product with the normal, then that will be equal to the JK current that is given by the Butler Warmer, right? Because ultimately I want to, the quantity that I talked earlier was the current and the flux. So I want my boundary condition in terms of the current and flux, right? So the current is actually given by the IK dot NK equal to JK, and the flux actually, in order to get the flux, all you have to do is just multiply with the Faraday constant, right? Or actually you have to just divide. I don't know why this keep on popping up. हाँ अच्छा okay fine ठीक है okay. And the similar thing on the electrode light side. And so this is about the boundary between the electrode and the electrolyte, but there is a more boundary, there is other boundary, right? And these boundaries are there at the here, here, right? So in case of here, the phi is equal to 0, the potential is equal to 0, right? The here you can specify some kind of potential, right? Or you can specify some kind of current, okay? uh, right? And that's it, I guess. I can talk about slightly more detail, but I think that is fine, right? So the only thing is you have to specify, this is also boundary, right? Top and bottom, So in the top and bottom there cannot be a current going out, there cannot be a flux going out. So ultimately at the top and bottom it is going to be I tilde dot n tilde equal to 0 and n tilde dot n tilde equal to 0. That is going to be at the top and bottom. There is no current that is flowing out at the top and bottom. So the flux as well as the current, that is going to be 0. Okay, fine. Separator you don't need to model. So when you are modeling as an electrolyte domain, then it is actually automatically taken care. There is actually one point that I omitted, but we can talk about this boundary, because the positive electrode, whatever the equation that you are solving for, actually will talk about only here. So for the positive electrode, this also will be a boundary. So here you also have to provide the boundary condition, and those boundary condition will be actually the current I tilde dot n equal to 0, and apart from that the flux tilde dot n equal to 0, because at once you have reached the separator, all the currents is actually now taken care by the electrolyte. The electrode particles are no longer carrying the current, so that's why you take the this particular condition here at the boundary between the separator and the electrode. My battery discharge. No, yeah. So you can, I don't know, like those who want to see, you can just search this paper and go through it, and if you have any doubt you can anyway ask me tomorrow or any day. Anyway, I will be here. So now this is was, but what is the issue? So if you see, whatever we have discussed is the most fundamental way of modeling the lithium ion batteries. Okay, so why not stop here? Why not actually go and again discuss something tomorrow? We can actually stop here, right? Because this is the most fundamental way of doing the things. So, but there is a lot of problem if we try to model whatever we have discussed today, right? The first thing, the problem is how I can make this nice looking diagram here. I can maybe make the electrode particle image even more fancier, but to actual battery, to get this image for actual battery, that is very difficult. That what is the actual distribution of the particle and everything. So it is a, so this information is actually very hard to get. One. Second, if these are not 8 or 10 particles, these are thousands of particles sitting sometime there. If I start modeling each and every particle, and these are non-linear partial differential equation, I have not gone into how do you solve it. Actually you have to discretize each of the particle with the finite element mass, then you have to apply Newton-Raphson, and then you have to solve everything, you have to do the implicit time integration and all those things. We are not going there. So it is going to be computationally really a big challenge to actually directly model whatever we have discussed. Okay, so we want something which is slightly more practical compared to whatever we have discussed. So this lays the foundation of the all other model, but this is not that much practical in general to actually model everything. Okay, so that's why we have to know, or we want to know, the homogenized model where we don't actually resolve individual particle, and we try to average out the overall behavior and try to see that. Okay, fine. Okay.